All right, go ahead and get started here. Unit 2 was a lot of the kind of pre-packaging that we are going to be doing for most of our data. So constructing a sample, understanding what kind of data that we are in fact looking at, figuring out how we can kind of visually organize a lot of that information as we go. What we're going to see in Unit 3 is an attempt to start actually putting some numbers to the data that we are collecting to, in fact, start doing the statistics stuff yet again. Now, a couple of kind of reminders, stuff that we have already covered, but that we will kind of see again here. We talked a little bit in 2.2 about the difference between a population and a sample. What does it mean for me to have a population under study versus like a sample of a particular population? What's the difference between these two?
Sample is part of the population.
Okay, so sample is like a subgroup of a population, and then how might I describe the population? Yeah, I think that's a really, really good way to do it. So our population is the maybe like every individual being studied. It's like the target demographic, and the sample is a subgroup of the population. We've seen that we can do statistics on both the population as a whole. We get kind of descriptive statistics when we are doing statistics with populations, or we can do statistics on samples of populations and try to use those statistics to make kind of conclusions about what we would expect to see in the population as a whole, using that as kind of inferential statistics. So inferential statistics was using statistics to make predictions or generalizations to a general population. Yeah, like that's exactly right. So for instance, the example that we worked with in Unit 1, we were doing a lot of stuff with regression lines. Technically speaking, the least squares regression line that we get, the regression equation, is a descriptive statistic of a population until we try to use it to make guesses, at which point we are using it as an inferential statistic from a sample. To that end, we also have slightly different verbiage that we talk about when we are referring to kind of features of a population and features of a sample. When we are talking about populations, we have what are called population parameters, which I am going to describe as like characteristics of the population. This is like a lot of population statistics. And for sample, we have what are called sample statistics, which statistics broad kind of view was like these are just our tools for analyzing data. A sample statistic is going to be, or sample statistics are characteristics of a sample. So think about like parameter. I mean, the alliteration is really, really nice here. We have population parameters, which are analogous to sample statistics. We're going to look at a bunch of these over the course of Unit 3. We're going to have a couple of different ways to kind of classify and characterize the information that we are sorting through. What we are going to be focusing on today is the parameter or the statistic that deals with measures of central tendency. So how do we describe the middle of our data, which often we'll use in place of like expected value and things like that, but we'll get into all of that as we go. Two kind of main ways that I would say we most frequently describe our data. What are kind of the two bread and butter ways that we talk about the center from a data collection? Median or the mean. Okay. We are going to lead with the mean here. So we've got our definitions here. We're going to talk about starting off what is going on with our mean or what is going on with the average. You'll see these two kind of used interchangeably. All right. What is the mean? Just very, very simple, very, very quick. What is our mean?
Average.
Okay, but like that's just another definition. How do we get it? Very good. So the mean or the average is the center that we get by summing up. We could take the sum of all data points divided by the sample space, sample size. Right. So if I have a collection, if I have a sample of 10 data points or a population with 10 data points, adding up all that data together, dividing by 10, you get your average. Nice and simple. All right, let's take this idea that's nice and simple. Let's put some nasty math characters to it. If you are confused by the symbols that I am using, I am going to show, maybe not in the case of the average, because I kind of expect us to have done a lot of work with averages before, but certainly in what we are about to do, if you have questions about like what a particular character means, please do not hesitate to ask. But also do know that I am going to give you the characters and then show them working. So I'm not just giving you like a formula to memorize. I want you to actually understand what the parts are doing and what they mean. Okay, so mean, average. Mathematically, we are going to be talking about, well, for starters, we've got this thing called X bar. We've looked at a couple of modifications on variables before. So for instance, in unit 1, we talked a little bit about y hat. What was the difference between like y hat and y? Why did we have to put this little caret over our variable here? Yes, but why don't we just say y is equal to ax plus b? Why do we have to say y hat? It could still be linear, but there's something different between y and y hat. Something very, very precise, some definitional difference. Oops. Does anyone remember? What does y hat? Does our regression line give us the actual observed values of y that go with the values of x that we see? No. So there's maybe some kind of error there. What does our regression line give us? If it's not the exact y value, then it is it's a prediction. It's a guess. All right, so we use y hat to indicate that what we are doing is guesswork. Right. Similarly, we're going to use x bar to say, well, these aren't actually the values of x that we see. Rather, this is an average of my values of x. So x bar referring to, in this case, an average. This is going to be the sum denoted by the sigma. This looks like a capital S in Greek. We'll set an index on our sigma just to make this very, very precise. So taking the sum of all of our x's and we are dividing it by the total number of things that we have added together. So again, this looks complicated. An index just means that like x sub 1 versus x sub 2 versus x sub 3 means it's like the first or second or third data point that we're looking at. So for instance, if my n was equal to 3, if I had 3 data points, I would add the first data point, the second data point, the third data point, add them all together, and then divide by that n, that's 3. Yes. Okay. So what we have just brought up is a really, really good point. Technically speaking, X bar is very, very specifically the sample mean. So this is right here, not used to represent just all averages that we could possibly see. This is a sample statistic. What do we use when we want to represent the population? Do you remember? Yes, right. So when we want to talk about the population average, which you will often hear me refer to as like the true average, it's like the actual average of all of our values being taken. Instead of using an X bar, you will use this kind of curly, my other ones are so much better. This kind of curly M here, which is the Greek for mu. Good news for us, this is not always the case, but it is for averages. The way that we find X bar, the way we find the sample mean, and the way we find the population mean is exactly the same. It's the exact same form. So there is no difference between the way we calculate it. It's just, you know, the n value for the population is probably a whole lot bigger than the one for the sample. And ideally, if our sample is good, if it's like an actual representation of the population, we would expect X bar and mu to be relatively similar. They should be about the same. What happens when they're not? Well, then we get to do a whole litany of hypothesis tests, and we'll get back into that later. That'll be like some Unit 5 stuff that we did. All right. Questions about our sample or population averages? Just taking an average, right? And I put some math verbiage of how to write that. But adding up all of our x's, dividing by the number of things that we have added up. Okay. This is, again, kind of hopefully review. We are going to be taking this idea of average and mean, and we are going to be modifying it ever so slightly. We're gonna be generalizing this a little bit. One of the key ideas that we see with our kind of mean here, one of the main things, is that every single data point contributes equally to the average. Right? Every single measurement of x influences the average in the same way. They all carry the same amount of weight. But there are many instances in which that is not necessarily the case. Maybe there are, well, a very, very easy example would be something like the way that your guys' grades are calculated. Getting a 100 on, say, like a quiz is not as impactful to your grade as getting a 100 on a test. Those carry different weights, even though they might measure to be the same value. Right? It's the same grade, but one of them is stronger than the other. One of them is more impressive. One of them impacts your average more than the other. And so what we have is kind of this desire to be able to account for what do I do if my weights for my different variables are different. What we want to calculate is called a weighted mean or weighted average. All the way down here. You're more than welcome to attempt the averages for the examples that you see here. I do kind of have some assumption that we'll have practice with just straight computing averages later, but I also do kind of assume that that is stuff that we are very well versed in at this point. And so I am slightly glossing over it to get to some of the meatier stuff here with the weighted averages, which are a little bit trickier. Certainly a little bit trickier. So weighted averages or a weighted mean, which is going to be an average where some values of x are more substantial than others, which is to say that they are weighted differently. Right. This is not the difference between like scoring a 90 on a quiz and scoring like an 83 on a quiz. This is the difference between scoring a 90 on a test and scoring a 90 on a quiz. Right. So there's something actually like fundamentally different about even if you get the same measurement of x, one of them is more significant than the other. We'll run with an example that I think it actually has a fair bit of utility. Let's say we need to calculate our final grade for the semester. We want to know what we need to get on the exam in order to get a certain grade, or we're just running through the computer breaks down. We need to do this all by hand. What would I need to do? Three different kind of variables are going to make up our final grade. There is the Q3 grade. There's the Q4 grade, so quarter 3 and quarter 4. And then there is the semester exam grade, the E2 grade category. Does anyone know off the top of their head how much the semester exam is worth? 15%. 40 would be a scary, that would be a very scary class. Yeah, we'll take a look here. So 15% for the exam, which means how much is left over for Q3 and Q4? 85. Is there a difference between, does like one of those count more than the other, or are they the same? They're the same. Okay, so like 85% split evenly between everything that we are looking at. And so if I wanted to arrange this in terms of my weighted average, I still want to add all of my Q3, Q4, and E2 together. All right. But I need my Q3 and my Q4 to be worth a significant chunk more than my E2. How much is a significant chunk? Well, if my E2 contributes 15 points to my final grade, and we know each of these is going to contribute 85 total. We know between the two of them, we're going to get 85. We know they're equal. Each one will contribute 42.5 points to my final grade. Then what we have here is a weighted sum. Now, a weighted sum is still not an average. Right? In order to actually average this, I would then need to divide by the sum of all of my weights. Right. So in this case, we have 42.5 points being allocated to Q3, 42.5 being allocated to Q4, 15 being allocated to E2. We need 42.5 plus 42.5 plus 15. We have a total of 100 points worth of stuff being allocated, which is effectively our N. You could think of this even in an unweighted case, if all of the weights are uniform, if all of the weights are just the exact same, then when we add up all the weights together, you should end up with just N. It should just be the sample size. So it works out even in an unweighted case, but this is about how we would do it. Let's take this specific example. Let us generalize it. If we are looking at our weighted average, we are taking the sum. Okay, so this gets to be a little bit annoying. The sum from all of our indices of all of our weights times all of our variables divided by the sum of all of our weights. Again, easy to get lost in the notation. All this is saying to do is we take the weight that goes with the first variable times the first variable, adding it to the weight that goes with the second variable times the second variable, plus all the way until we see that final weight attached to that final variable, divided by all of our weights being added together. Questions with the notation before we take a look at another example here? I want to take a look at another small scale example of this. I think this really helped my fourth period kind of internalize some of what we're doing. If we take a look at the data set above, where we just have like our normal average, we're going to take a tiny subsection of this. Let's just consider these first two values, 124 and 71. If we were to compute the average between those two values, you would add them together, divide by 2, done. Nice and easy. Well, let's say for whatever reason, I want that 124 to be twice as important as that 71. Okay, so there is not this kind of equity. These are not weighted the same way. I need this one to be twice as important as this one. What weights could I attach to 124 and 71 in order for me to see that 124 effectively showing up twice as frequently, or whenever it does show up, have it be twice as impactful as the 71? Okay, we could do that. What would then the weight be that we attach to 71 if we're going to do 18 to 124? So 0? Yeah. So then it's not counted in our average at all. Okay, you're jumping through too many hoops. All right, so that kind of mental, you might be right, it might work. When I'm saying attach, I mean that there is something that we are multiplying this particular value by in order to give it more importance. All right, that kind of hoop jump, it might work. It might turn out that that is in fact the correct way to weight it. I would be hesitant to do it that way, especially if we had like 5 different variables that we were trying to juggle. That would become very, very difficult to do. So you might be right. I would expect it to be lower, but either way, there's a way that we can do this multiplicatively. What can I say if I want 124 to be twice as important? Well, what if I attach the weight of 2 to 124? If I'm attaching the weight of 2 to 124, if it's twice as important, what weight would go to my 71? Twice as important. I need 71 to show up once. Right? Every instance of 124 essentially acts like 2 instances of 124. Every instance of 71 acts as 1 instance of 71, and we take the sum of our weights. That is the weighted average, yes. That would give us the weighted average where 124 is twice as important, is twice as valuable as 71. Where we want it to count for 2 times the amount that 71 is counting. You could also think about this in terms of percentages. I think that that's not a bad way to think about it. If you divvy up, break apart this fraction, which can be a little bit tricky, but if you were to break apart this fraction, you would see that 66% or 67% of our data is being accounted for by that 124. 33% of that data is being accounted for by that 71. That's what we're trying to say, right? We want the 124 to be contributing twice as much, 67% rather than that 33%. That is our ultimately. And you could do the same thing here as well, and you would get the exact same thing. No questions. All of this is like, yeah, I'm completely rolling this notation here is like super easy, and we completely understand the weights, no questions at all.
When do you use weighted average?
When particular variables are more important than others. So for instance, getting a quiz score versus getting a test score, where you don't have uniformity between how much each value of x gives.
So can you give like an example of
I just did. Yeah. Weighted averages for a grade would be a fantastic example. We're going to look at a couple other examples here, though. Okay, so we'll just jump into some examples then. All right, we are being asked to figure out the weighted mean between 3 different models of automobiles being sold. And we are given the data that we see. We're also asked to round to the nearest dollar. We're not going to do that. We're just going to, it gives us a nice clean kind of money amount. So we'll just figure out that. But, you know, worth noting that it does in fact ask us to do that. Now I could use what I see here as a frequency diagram, right? I could take like this frequency for this particular value of x, this frequency for this one. That wouldn't be too hard to do. We could do this like a normal average. There's nothing wrong with that. Where I could do like 20,000 plus 20,000 plus 20,000, you know, 9 times. And then do the same thing with 23,000, same thing with 15,000 over and over again. But let's try and do this in a little bit more of a condensed way. if I'm going to add 20,000 to itself 9 times, then what is maybe an easier, faster way to write that? 9 times 20,000, right? So rather than doing it by hand like this, we're going to say that our weighted average is going to be 9 times 20,000. Okay, so the 9 is the weight, the 20,000 is the value of our variable. Okay, well, what weight do we need to attach to 23,000? How many times do we want this 23,000 to be added up in our total kind of lump sum? We need it to be 10 times. Okay, and then lastly for 15,000, 13. All right. And then we're dividing by, again, here we've got like our total number of sales we could think about. How would I find all of that? Yeah, how would I find total quantity? Adding up all the weights together, right? Doing 9 plus 10 plus 13, this ends up being dividing by 32. Okay. So why is this the same as what we were doing with the grades? This feels like kind of two different processes. Like this is one where, yeah, we could have just taken a normal average, right? We could have just done 20,000 added 9 times. And we could have done 23,000 added 10 times. Like that's not, it's annoying, but it's not particularly hard. Whereas like it doesn't make sense to do our Q3 grade 42.5 times. Like what does that mean? Why are we doing it that way? Really the connection here is the idea that if I were to split apart this fraction, each of those weights that I would see represents the fraction that I have that I want this particular value of x to contribute. So for instance, if I want to know what fraction of my sales go alongside this 20,000, then I need to take that 9 out of my total number of sales, which you said was 32, times this variable 20,000. This is my weighting the 20,000 to be about 1/4 of my sales. We're saying about 1/4 of our sales are coming from 20,000. We're saying that 10 over 32, 10 30-seconds, so a little bit more than 1/4 of our sales are coming from 23,000. And then a little bit more than 1/3 of our sales, I assume, looks like a little bit more than 1/3, are coming from this 15,000. That might even be like 40% of our sales, something like that. All right. Notice how we want the 15,000 to be weighted more heavily because it accounts for a higher percentage of our sales. Notice how we want the 20,000 to not be weighted quite as heavily because it accounts for a lower percentage of our sales. These are the exact same thing. What I did here, that's just a really quick algebraic manipulation. This is just a way to more clearly see that, in fact, what we are doing over here and what we are doing over here is the same. It's the exact same process. Questions? No questions at all. This is like one of the harder math things that we'll do. By far the hardest one we'll do today, for sure. So this is the opportunity. This is the place to ask questions if we have.
So
Yeah.
we did it as a fraction, 9 over 32.
Mm-hmm.
an hour 30 minutes a day.
Sure.
So besides obviously simplifying, is there like any bigger purpose as to like why you do it as a fraction?
No, this is just to say that like these represent like percentages of our total number of sales. Right? So this accounts for like 40% of our sales, a little bit more probably. I don't know exactly what it is. Well, no, so this represents 40% of our sales, and $15,000 is what we are getting for 40% of our sales. So we attach that 40% weight to this $15,000 of sales. Likewise, we have this, roughly like 30-ish% amount of sales that is attached to our, 23,000. And we have this 25% of sales attached to the 20,000. Which is I think this is a more intuitive way to kind of construct it, where each one is a decimal rather than like a whole number. So I wanted to show you this like more conceptual way to kind of draw it up, right? Where each of the weights is actually a fraction of our total, whatever it is that we are looking at. All right, should we look at another? I want to give you guys, we'll say like 5 minutes to attempt this setup, and then we'll go over it together. In this case, we have weights that are determined by the number of credit hours that a class is worth. So for instance, you would expect a class that is worth 4 credit hours to contribute twice as much to your GPA as one that is worth 2, and kind of so on from there. So using that in order to kind of calculate this cumulative, or not cumulative, but this weighted GPA. Perfect. Yeah.
There's 4 classes. Oh, there's 4.
What did you do?
Nothing. Don't look at it. Did it backwards. 1, 2, 3, 4.
Did you just miss a class?
No, I did backwards. I switched the.
Well, that shouldn't matter.
Oh, okay, then yeah, I missed the class.
But you can also combine them, right? Like you can have like 5 total credit hours that are being accounted for with like getting an A in 2 classes.
Yeah, I was
So,
just sociology.
yeah. I was gonna say, yeah, the order shouldn't matter because all of this is commutative. That looks perfect. And then just like talk about the other side. You want to add all of the weights together, so you'll do the 5 credit hours. So what we're adding is the credit hours. So the 3, the 4, and the 2 are the values of X that we're taking, and the weights are the credit hours. So yeah, you did it backwards there, and you're gonna add all of them. So even like repeated values, you'll add them. Yeah. Nope, this looks good. You're plugging your calculator, see what it equals. It just makes sure when you do the division at the end that like you're dividing the whole numerator by it, which you can do by dividing the numerator and enter and then divide it by it. Yeah, that looks good. And then you plug out your calculator, see what you have. Yeah. Okay. Looks good so far. And then what are we going to divide by?
5 plus 4 plus 2 plus 4.
Perfect. 5 plus 4 plus 2 plus how many credit hours was the last one?
5 credit hours.
5 credit hours, yeah.
So she argued these are 50.
Mm-hmm.
this is English, after 3 credit hours,
Mhm.
or the name, so
I agree.
4,
Yeah.
4, 3, I got you. Doesn't make sense.
So this one would be, yeah, so this would be 3, and then this one would be 2.
But I think, yeah, this is something is, here.
Yeah, it's these 2 right here. These 2 look good. I would double check those 2 right there, those last 2 classes.
Sorry, but the thing is, I put 5 credit hours, and, or a B, so I put 3.
Yeah, that looks good.
Here, I put.
Okay, yeah, you're right. This should be, this should.
So I don't get, I mean, like, I don't get 2 things that I don't have. One, like, how do you know, like, which one to put in parentheses?
So the value of X in this case is the grade, right? Like the variable that we are measuring is grade. And so the value of that variable, the variable is going to relate to is the A. The B, in this case, the numbers, the 4, the 3, the 2, and the 1, are just our ways of putting it in order to getting an A.
So they go and try and.
Well, sure. I mean, order ultimately doesn't really matter, but those are the weights. They're the weights.
As long as-
Or no, they're not the weights. They are the weights.
Like writing or the so as long as.
Well, yeah, the order doesn't matter.
As long as both of them.
Yeah, as long as they're consistent.
Okay, so we actually have.
Commutative. Okay. This looks great. Yeah, this looks great. Yeah, this looks great. Yeah, so in this case, the variable that we might measure is an A, it's an B, it's a C. Well, I mean, so exactly what you have here, the value of that variable, the number that we attach to get an A is
It doesn't like when I'm right.
and then the weights are the credit hours, exactly right. So for instance, we have a contribution of 5 going to this particular, this A.
I like the
Perfect. Adding, summing all that up, and it was 13, and then you actually, you don't even need this, this is just another way to write it.
You're a nerd.
You can just straight up
Until it feels like.
Yeah, and the only thing you need to make sure is when you plug it all in, I would do all of the numerator and then you enter it and you divide it by 2, just so that you don't mess that up. You just want to make sure that it's everything. Yeah, so I would do like 5, I would do it exactly.
I mean,
Or,
sometimes I
and
say
it'll do
things
all
like
the
I really sad that I said them. But
Yeah.
like, it's just-
4. That's like our weighted score, and then we're dividing that by.
Because she couldn't do it, and I filled out her entire fast one.
Yes.
Thanks.
Well, the paper
This is why you have no letters.
Yes. We should have a fair bit of time at the end.
Thank you.
Okay, let's take a look. Overall, looked really, really good. You guys did a good job with this. Let us arrange this. I'm going to do this in a table first. I didn't see a lot of people doing this, but I do think that there is some utility behind doing this. We're going to consider the grade that we get and the number of credit hours that it contributes to. All right, so we saw 3 different grades. I'm sure we could talk about D's as well, but there weren't any, so we don't really need to worry about that. So how many credit hours did we see going to A's? So we see 2 from sociology, and then what else? English or whatever.
Yeah.
3 from English, so a total of 5 credit hours being contributed to this A. If you didn't do this, if you did class per class per class per class, you get the same answer, so it's fine. It ultimately doesn't matter, but I'm showing that, hey, we could have also grouped this as well. How many credit hours are going to account for our B?
5.
5. How many for our C? 3, I think.
3, yeah.
3. And then how many classes do we get? This is more demonstrative. I would not expect you to have this. How many get Ds? 0. Cool. Okay, now we need to turn this into the actual quantitative. How many points do we get for getting an A? We get 4 points for getting an A. So this is going to be, in that case, our weight is 5, right? The credit hours that we are contributing. 5 of those credit hours give us 4 points. How many of those credit hours are giving us 3 points? 5 of the credit hours are giving us 3 points. How many credit hours are giving us 2 points? 3 of the credit hours are giving us 2 points. And then how many credit hours are giving us 1 point? 0. Which would be like the D's that we got. Very good. Notice that this weight is just 0. Right? The number of Ds don't contribute to this GPA because you didn't get any Ds, so we don't need to worry about it all that much. I am purely showing this to say, like, hey, there were other values that our variable technically could have been. That is also technically counted for in our weighted calculation. It's just the weight that we attach to it is 0, so it disappears. All right, so 5 credit hours, 5, 3. How many total credit hours are we looking at here? 13, which was 5 plus 5 plus 3. And so our weighted GPA is going to be, I get that this is 3.15. You could have also done each class, and that would have been fine. I did each grade value, and that was also okay. It combines like terms. When you do the 2 times 4 plus 3 times 4, you get 5 times 4. If this were uniform, if every class contributed the same amount, we wouldn't have these weights. Instead, we would just do like 4 plus 3 plus 4 plus 2 divided by 4. And this would be our unweighted GPA, where every single class is contributing the same to our GPA, the same amount to our GPA as another. Which is actually like the difference between a weighted GPA and an unweighted GPA. One says all classes are the same. One says some classes are worth more than others. And so we see these weights to adjust for that. All right, questions with our weighted average example? Not too bad. Horrible. Somewhere in between. Which I guess would be bad if my best metric, if my highest value is that. Feeling okay? Cool. The other stuff is fairly straightforward, but we will go through it while we are here. Oh, I should have showed you the percentages as well. Whatever, it doesn't matter. That's fine. Okay, so average was the first measure of center that we talked about. What was the other one that we mentioned at the start? Mean and median. Okay. How do I find the median from a data set? Yeah, so this is a range from least to greatest, and observe the middle value. All right. If we have an odd amount of data, we have the same amount of data on the left and the right of a particular value, there will be an actual middle value. But in the second example here, notice we have an even amount of data. So as I go through and arrange it, as I start with what, 648, and then 656, and then 864, and then 901, and then 956, and then 1132, and then 1232, and then 1303. So arranging in order, least to greatest. And I think the strategy that you guys have probably seen, the one I use, the one that I've been taught, and it's kind of annoying because there isn't like a way to, for at least I don't have a way to do this really fast, is we just go through, we strike off one from each end until we reach the middle. Problem is here we have an even amount of data. There isn't one exact value that sits perfectly in the middle of everything. What do I do when I run into a situation like this where I have two values at the center of my data? Take the average between them. Very good. So this would be 901 plus 956 weighted equally, and we are dividing by 2. I think this works out to be 928.5. Sure. Yeah. Ta-da. If there had just been one value, we'd circle that value. Yeah, so an interesting thing to observe. First of all, yeah, we have this decimal, which is kind of just a consequence of adding an odd and an even and getting an odd. But I think more interesting, 928.5 doesn't come from our data, right? Normally the median is like an actual value from our data, but when we're doing the average like this, it's possible that we get a value that sits between two values in our data rather than something that's from our data itself. That's okay. If we had an odd number of numbers to work from, then we would actually land on a value. There would be a particular value, and that'd be great. But just as a consequence of taking this average here, we end up with a value that it's not necessarily a part of our data. What is the context? Oh, yeah, way out. Yeah. Counterbalance that with, you know, admission fees for amusement parks. The true dichotomy. All right, questions with median? This one's, I think, more annoying than average. I will tell you guys at the end here that there's a very easy way to do this, which is cool. But of course, you know, have to torture ourselves a little bit before we get to the end bit where everything's nice and easy. Awesome. Okay, for our mode, for our next kind of measure of center here, sort of a measure of center. We're going to see that it often acts like a measure of center as we kind of get into this. What is the mode of our data set? Yeah, this is like the number, maybe with the number with the highest frequency, to put it into terms of what we just did. So the value with the highest frequency Okay, we have some sub definitions here, different types of modes that we can have. Unimodal, think unicycle. How many modes would we expect to see from data that is unimodal? One. Like bicycle, how many modes would we expect to see from a data set that is bimodal? Two. And multimodal is just like a catch-all if we have more than that. So if we only have one value, there is exactly one value that is definitively the highest, then it is unimodal. If there are two values that are tied, bimodal. If there are three or more values that are tied, multimodal. And then if there isn't a value that has a highest frequency, maybe every single value shows up 20 times, right? Completely uniform distribution. There is no difference between the frequencies that we see. Then we have no mode. So it's not no frequency. It's that all of the frequencies are the same. There is no highest frequency because they're all equal. Yeah. Slight point of clarification that I want to make. Technically speaking, unimodal and bimodal need to kind of match. So for instance, if I have most of my buckets filled with 7. If most of my variable instances show up 7 times, and then I have one variable that shows up 32 times, so a lot, very clearly going to form a mode, and then one variable that shows up 31 times. Technically speaking, it is unimodal, technically. But for all intents and purposes, it would be bimodal. And in fact, if we were to look at the distribution that we would see if we were to do a histogram for that particular case, then what we would see is exactly kind of what you would get, where we have two kind of distinct peaks here. That each represent a cluster of data. Yes, maybe this one is slightly taller than the other, so maybe technically there is a mode. I would look at this and view this as bimodal, though. I would say that this is a bimodal distribution, even though maybe there's a little bit of difference between that. Maybe it's technically unimodal, but it is functionally, for all intents and purposes, bimodal. So a little bit of imprecision that we can introduce there, which mostly just comes from like, hey, we did a sample and it had a sample size of 55 and 33 of them turned up this way and 32 of them turned up this way. That's about the same. That's about the same.
Are we going to review all the tests?
We'll have a little bit of time at the end of today if you guys have questions that you want to ask. Okay, one last measure of center, and that is the mid-range. This is maybe one that you haven't seen before. It's not particularly all that crazy. Mid-range, the middle of the range, think like the center of the interval that we are working with. This is just the average between the minimum and the maximum value. It doesn't care about like any kind of distribution. We don't care about, are we closer to one or the other? Do we have outliers? Things like that. This is very, 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 very simple. So for instance, what's the minimum value from this data set? What's the largest value? 9. Average of 1 and 9 would be 5. 1 plus 9 is 10 divided by 2 would be 5. Done. So very simplified, and it is what the name describes, right? It is just very simply the middle of the range. It is the middle of what we see for the largest possible value and the smallest possible value. It is smack dead in the middle of those. All right, questions with our central tendency? Okay, let's take a look at this example here. I want you guys to go ahead and get out your calculators. I want you to go to Stat, and I want you to go to Edit. And in L1, I want you to enter this exactly as you see it. So 62, and then 72, and then 66, 79, 73, all the way down. So 24 different data points. All in. You will notice that they're not ordered. So trying to do things like figuring out the median could be really, really annoying, things of that nature. Looking at trying to figure out modes could be really, really annoying. Go and you're going to pick either sort A or sort D, whichever one you want. Doesn't really matter. This is a calculator function. You need to plug in a list to sort. So once you have sort A or sort D selected, you're going to press second 1 to sort L1, and then you're going to hit enter. Well, fill out the list first and then. When you go back into your list, you will notice that all of the values have been arranged from either largest to smallest or smallest to largest, depending on whether you did sort A or sort D.
You do sort what?
Sort, you can either do sort A or sort D, so you go to stat. Either one, yeah, sort A or D. And then second one, we'll do L1, and then enter, and then go back into stat, take a look at your list, and you will see that it has been sorted for you. Yeah, so you don't have to do this by hand, which is nice, because that's the most annoying part, is like going through the list, realizing, oh, I missed a value. What on earth do I do? Well, I have to like go in and carry it, and then it gets messy, and then it's annoying. Okay, so go back to your list, and you'll see that it has been sorted. Now, if we wanted to do like modes and stuff, I think arranging by order is a really nice way to see repeated values. So that's very useful for that. We could certainly then take this and do the median. Go back to stat, and this time go over to calc, and select one variable stats, and run your calc. Calc. Run the calc. This is pretty much all the information that you are going to need for this. You'll notice the very first thing that it tells you is X bar. So right away, it tells us that the average, the mean, is 67.54. Okay? It might be rounding, or you might have had a data point that you entered that was like slightly too big or something like that. Okay. You will also notice that it tells you the median. In this case, we see a median of 67. Of course, 67 is not a data point that we entered. So where did that 67 come from?
From adding the two.
Adding 2 and then dividing, probably the 66 and the 68, falling somewhere between those two values. In fact, if you did this by hand, you would have to add 66, 68, divide by 2, you get 67. Cool. It also gives you the minimum value and the maximum value. You can take the average of those two to find the mid-range really, really easily. The only thing it doesn't give you is the mode, but that's why sorting the data is really, really nice. You don't have to sort the data to do the one variable stats, but you could then go back and look at the data and really easily find the mode within the data there. So just some very handy calculator features that allow you to basically do all of this automatically, which is nice. Lets us bypass a lot of the annoying bits of finding these values. All right, any questions from 3.1?
Yeah, the average, I mean, it's showing me 12.7.
It should say, you might be using the wrong list for the.
That one is.
You
Probably enter either
the positive number shows the post
or
multi-mode.
you put in values that are,
Right.
it either means you missed a value or that you put in something in about entering tools.
74 common, 72 common.
No,
So there's multiple of them. Is it a one? Yeah, but we have.
No. I'll read the second one.
Do we have to?